So, hi, my name is Clemens. I work at Microsoft. I am the architect for messaging at Microsoft in Azure. So we have a few things that we run in Azure. I've been in the. There's a lot to read. Don't worry about it. I've been in the Azure team for 9 years now, which is funny because Azure is 9 years old. So one of the first services that or the first service that celebrated its 10th birthday was at the end of last month, Service Bus, because we had our first public outing of that service exactly 10 years ago on May 31st, 2006. So we've been around for quite some time. And I didn't bring the brag slide, but our messaging infrastructure, the broker infrastructure that we run, currently runs about 350 billion transactions per month. The Event Hub, I'm going to talk about Event Ingester briefly, also currently does about 3.5 trillion transactions per week. So we run a fairly large messaging system, and so messaging is something that we're building. As it happens, since I'm a little bit older, I've been seeing the cycle. Now I'm seeing the cycle the second time. I see this microservices thing, and I'm like the girl in Jurassic Park in the control center. Like, this is a unique system. I know this. I've seen these things. Turns out a lot of these slides that I'm going to show you today are 12 years old. We'll see whether you can spot which of them are. And I have a lot of slides for you, so this is going to be a lot of material. I have 70 slides, so we'll see how we can get through them. And what I'm going to start with is my notion, our notion, of services and what service means. Because there's a very clear understanding that we have in services, and you'll also see why, because I'm going to use Azure as a showcase for what services mean, because we built a system that consists of 80 services that are all workload services that not only you can depend on, but also that we depend on each other. So it's a very large ecosystem of services that we built on top of it, where we build on top of each other. So it's not something that's internal. No, it's something where workload teams, 30 people, 50 people, are actually building workload services for you, but also for other people to consume. And that can only work with particular approach to how we build those services. I want to tell you about that, and also want to tell you about messaging. I want to tell you about protocols, and want to tell you about choices. And it's going to end in a very simple summary picture for how you can go and structure services and think about it. So what is a service? This is my definition. It's owned, built, and run by an organization. That's the first defining criterion for a service. When we talk about service, it's something that is about organizations more than it is about software. It's about ownership. It's about autonomy of that organization to go and deploy and run stuff. My team runs a service. And what means run is there is no ops team. We run that thing. We build it, we deploy it, we run it. Second, the service is responsible for holding, processing, and distributing particular kinds of information within the scope of a system, and it has authority for something. In my case, we build technical platform services. We built the messaging service. And that messaging broker, there's one in that platform, and that's our authority. Yeah, we have two queues, and another has a different purpose. But in an organization, the larger organization, there is one particular service that does one particular job. Now, there may be some overlaps, and there will be some overlaps due to practicalities, right? Companies merge, then there's a thing that calls, there's a trap that's called the customer service. There is no one customer service because each sub-organization has a different notion of what a customer is. But for that particular notion of what a customer is, there's one service and there's one team that owns it. Every service can be built and deployed and run independently, meeting defined operational objectives. We'll talk about that too. It communicates with consumers and other services, presenting information using conventions or contract assurances, which means there is a contract, there's agreement about what that service and how that service communicates. It protects itself against unwanted access, there's security, and its information against loss, there is safety for your data. And it handles failure conditions such that failures cannot lead to information corruption. So failure handling is part of the definition. That is a service in my view. Whether that is micro or macro or whatever that is, actually doesn't matter because all those things also stack. Your service that you built is a composition of all the services, downstream services that you consume. I said scope of a system, let's go and define that too. A system is a federation of services or other systems aiming to provide a composite solution for a well-defined scope. A airline booking system, a video distribution portal. Some of those services may be shared amongst others, and that's truer for platform services than it is for workload services that provide business logic. So Azure Storage is a service that can be easily shared across many things because it's not very specific. A customer service, again, that's the trap, is unlikely to be shareable across anything that is not exactly that organization that has that particular notion of what customer is. The solution scope for that service may well be not just technically motivated, but also may be motivated by business, technology, policy, law, culture, and other criteria. So you may go and set up a separate service, a separately run service that may consist of similar code that needs to be run separately by a separate team because of legal requirements, because of regulation, because of all kinds of, it's not only technical requirements, not only pure business requirements, but there's also other requirements for that as well, which cause a different system to be set up in whose scope services run. And a system may appear and act like a service towards other services. So that's like a SaaS platform. Office 365 is a service. But it's a very huge conglomerate of actually built-in services that you never see because it's got one pretty skin on top of it. So much for definitions. Service does not imply any of that stuff, in my view. So if someone says you can only do services if you use Docker, that's nonsense. If you can only do microservices using Kubernetes, that's nonsense. Same for JSON or XML or SOAP or REST or any of those things. It has nothing to do with it. Service is really something that talks about organization, how you scope stuff. And it talks about ownership, and that's something that's important. That's architecture. This is implementation. This is design. Service is about architecture primarily. We'll get to the design piece in a moment. Before that, let me warn you of something. Because when we tried that service thing the last time, like 1998, 1999, when we came up with this notion of service orientation, and we were kind of like, Microsoft, were kind of on the forefront of that, something happened. The ESB people came, and they messed it all up. So we did a good bunch of messing up in that whole story with W star, specifically W security. W security was so complicated, nobody understood it. It's awfully hard to implement. So I can see why people didn't like the whole SOAP business because it was too hard. The ESB though, that made everything really terrible. Well, how did the ESB come about? ESB had lots of marketing dollars behind it, and vendors with vested interest to go and sell you that thing and sell that thing into the enterprise. So you could buy product A, I don't want to bash the competitors. But you could buy those products, and they were now the central part of all of your integration. Interestingly enough, those vendors are now selling you the API gateway, which is exactly the same thing. So let's take a look at that for a moment. So that bus that you're being sold, the enterprise service bus, is not a bus, it's a hub. Typically, it's four machines that sit somewhere in the corner, and through which all of the message traffic runs. That's not a bus. That is a bottleneck in the enterprise. And the more and more you add to it, the harder that thing gets to scale. That's the reality of why SOA failed. Is a failure in many people's view, is because it has become coupled to this notion of an ESB. So what are the promises? The promises of these ESBs is that you have centralized deployment and config integration, and you have all these adapters, centralized service governance, centralized management of routing, centralized repositories, shared assets, all wonderful centralized. You can go and have, turn all the levers in that one place. The dilemma is, well, at scale, and if you really want to have a lot of services, if you run these where you now have mobile clients which show up in hundreds of thousands, you have 80 services which need to depend on each other. If you want to go and centrally manage all that stuff, that's getting really difficult. Who is maintaining those 4 servers? Who is actually owning all that stuff? What this turns into is the central IT organization where you have to go and file a change request for the ESB to go and change an adapter or change some configuration. So that's a horrid idea. If we had done this in Azure, just as an example, with all the services that we have, all the teams that we have, with 5,000, 6,000 engineers who are working on this, who owns that centerpiece? Who owns that big rendezvous thing in the sky? Who owns the integration application server that everything runs through? Nobody can. It's too hard. So that whole idea of having an ESB, of having this big thing that's sitting in the middle of your enterprise and that everybody rendezvous on, is giant nonsense. And that is a failure. That is the failure of not of the notion of services. That is actually the failure of the concept of centralization. So microservices is the resurgence of services as we thought them up in the late 90s and the beginning of the 2000s, before all that ESB nonsense happened. The API gateway is exactly the same trap, so don't fall into it, because we may be messing that up again. So be aware, if someone says to you, I want to have, here's a centralized managed API gateway, that's the same thing. So that much as a word of warning, just because I have you. Now, case study, Microsoft Azure. How do we build stuff? How do we run these? So we have a large number of feature services. We have probably 200 services altogether, including the internal ones. I think we have 85 public feature services that we have individual names. And of course, there's a lot of stuff in the back end that helps us kind of running the system, right? Just as much as the Netflix folks have a lot of services that you never know about because you're consuming their pretty front end. We have a lot of services in the background that also we're running. And then these are the shared backend services, such as billing, such as diagnostics pipeline, which does trillions of events per minute. We're all independent teams. So my team is, depending on how you count, 50, 60, 70 people. We're shipping completely independently from everybody else. We don't need to announce to anybody that we're shipping. We don't need to announce to anybody that we're patching, because we're making promises to our internal folks and we're making promises to the world. The clear advantage that we have as a team is that we have an obligation to the public, because we're shipping a public service that also internal parties rely on. So we have the obligation to upgrade the system, which is stateful. It's a message broker, under load, maintaining SLA. Maintaining SLA means we need to have 99.99% uptime, 99.99% reliability through the upgrade process. And that's something that we're making a promise about, and we have to go and uphold that. We're shipping features and fixes daily. There's a deployment going on all the time. There used to be some time when the executives got on stage and were presenting Azure that there was kind of a change ban that no longer exists. Like there's deployments going on when Scott Guthrie gets up on stage at the Build conference, there may be just some upgrades running, because there's no ban on all this. It just needs to work. 28 plus core data center facilities. I think we're up to well over 30. Our total data center footprint is 200 that we have, including the CDN nodes and what else we do in Microsoft. But Azure is currently in 28. We have our service has at least 2, sometimes 4, sometimes more clusters in each of these data center facilities. And those clusters are between 16 and 256 machines with 2 to 4 cores each. So we run fairly large clusters in those setups across those systems. And what they do is they move messages just in a clever way. The only way how this can work, so I just talked about us, but us meaning us, the service bus team, the messaging team, we federate with everybody else. So we rely on storage, we rely on compute, we rely on the billing pipeline, we rely on all those other services. So everybody needs to be able to go and deploy themselves. Everybody needs to go and have the same agility. And that's something that you can only achieve if we have the right principles. So what I told you at the beginning, the definition, that is the core of those principles. And so I want to explain more and how we get to those principles and how we think about those. So a service. Let me go and dive into more from a conceptual perspective because that matters. And this slide is actually, and this is something that I'm really glad about and proud of, I have to say. This slide is literally 12 years old. That was right then. It is right now. And that's the fabulous thing. We were right about this whole thing 12 years ago, about autonomy, about doing this in the right thing. We built the services in that way. This is not a new movement. This is proven principles. And that is why I'm so excited about microservices. I'm not excited about the name, actually, but I'm excited about the fact that we have taken services back from this mess that was the ESB and are rediscovering the principles. This is a cycle I'm really excited about. So a defining property of services is that they're autonomous, and that autonomy speaks about teams. Autonomy is independence. A service owns all the state and immediately depends on the managers. All the data belongs to that service, and only to that service. The service owns its communication contract. The service owner owns the contract, makes a promise, and if it wants to make a change, they can make a change. But there's no central committee that defines what that contract looks like. The service team owns that communication contract. The service can be changed, redeployed, or completely replaced at any time. Service has a well-known set of communication paths where it announces itself. The service shall share no state, no internal state with others. There's no common data store. There's no shared in-memory state with any other services. If you do this, then you don't have a service. You may have a tier, but not a service. I'm going to get to tier and services and layers in a moment. And there can't be no sideline communication. Then we'll also talk, and I'll have you have a picture in a moment what that means in terms of and why that's bad. Interdependencies. Your service owns its own uptime. If you depend on a storage service underneath where your data is stored, and that service is gone, that's your fault. Because you ought to have a replica of that data somewhere else. Or you should at least minimize the risk such that maybe one of your partitions goes down, because that goes down over there. But you should go and spread the risk around for your downstream dependency so that you can go and stay up. And you should, if you stay up, if you go down, then at least be upfront about it, right? And give proper errors back. Don't just crash. Like, you need to expect that all the stuff that is downstream from you is not available. It may not be available. So what is your plan for when that happens? So that's something to be really conscious about. You own your own uptime. It's not something that you can go and blame on others. And an autonomous service honors its own contracts, because you can only be autonomous if you have confidence that you can go and upgrade. And that means you made a promise in the current version, and you now make an upgrade. Well, the other people who are talking to you don't know about your new features and your new contracts, so you have to honor the old one. And in most cases, there is a people contract that goes along with this, which means we're going to sunset this API in a year. And that's how much warning other organizations need. And that's our policy, is to say, we actually give you a year to go and change things. And that might sometimes even be slow. So yes, you can go and rapidly evolve your services, but you need to all honor backward contracts. And if you look at many of the services that we have, sometimes they actually honor contracts 20 versions back, because we can't break the clients. bits are deployed. Bits are shipping with other software. So honoring the contract is the way how you achieve autonomy for yourself. It's something that is a required discipline. So why is sharing data stores bad? Very simple example. So you have two services, and they store data. They retrieve a primary key, passes that onto the other service. That other service now relies on the same store, right? Token, data. Now the problem with that model is that service can never go and depend on the other store, right? You can't move that service over to the other store because they have a secret relationship with each other. They share primary keys. They can't. They have to pass the data around. Literally, when you make those two services are now coupled. Why is that bad? Because it's one store. You can't pull it apart. You can't scale it up. You can't partition it. You can't do any of the things that one of the services might want to do because the other one depends on a particular relationship with them. So these are not two services. These are actually two modules which are looking at the same database. The nice thing also is that data store decoupling enables evolution. The contract piece not only is valid for talking to you to the service through the REST API or through messaging, it's also true for the relationship towards the data store. Because the data store also has a contract, has a schema. So you have an evolution that goes on where you now need to have new features. And if you have new features and you need to have the data store change, well, then that data store can very easily change if you have the store separated. So the decomposition of services from a monolithic application into services means that you're breaking up the database. Otherwise, you don't have services. It must mean you break up the database. And breaking up the database, there's a whole talk that I would love to give, and that's a 3-hour talk probably, about data patterns. Look at your database and differentiate between the data that is written, that's read, write, and hot, and that you write once and never change again. Right? Think about what the data does. There's some data you can easily replicate throughout the world very easily, and the transactional core is very, very small in most databases. So you have to triage your database. That big data model with 170 tables or 700 tables is dead if you want to do services. Also, services have different requirements in terms of scale. And this is where we also get to tier concerns later. You have a service that deals with front-end traffic from mobile devices and from a mobile app that you just shipped. And you have a back-end service that just accepts whatever, bookings, right? You have a travel service. That travel service with a catalog is going to serve a ton of requests. Those travel bookings are going to come in, fairly rarely. Those have completely different scale concerns, and you can go and build them differently. So you have a service B, service P. This slide is actually 15 years old. The service becomes overstressed. What do? And they're all sitting on the same machine. We split them up. 2 machines. What is the requirement? No shared in-memory state, no shared in-memory dependencies between the two. They need to be autonomous. The service still runs hot. What do? Well, you shard it across machines. So in the simplest case, you cannot have cross-instance state. This is where the notion of stateless shows up, where you don't have any interdependencies between those service instances. They don't share state in the simplest case, because the more sophisticated our systems get, the harder gets the stateless thing. And the stateless thing is really just a lie, mostly, because it talks about the length of the session. It doesn't talk about anything that's happening at runtime. Stateless means, commonly, you make a request, and after that request, you forget everything. The length of the session is 1. But we have more and more sophisticated systems where the length of the session is longer than that. So what are we going to do with that? So there's infrastructure that we add for this today, where modern clustering infrastructure can allow for easy and consistent state sharing, failover of ownership aspects of partitioned workloads. One of those examples is something that we have in our cloud and also available for on-premises, also in preview for Linux, and it's called Service Fabric. And Service Fabric is a clustering fabric. And there's many other examples of DHTs, distributed hash tables you can go and find, which can also go and replicate that kind of state across machines. But I'll give you an example of how the Service Fabric works in our system. So this is a generic picture of a gateway that has a stateful compute tier behind it and has a storage tier behind it. Turns out the service that we built, our broker actually looks like this in that way. So we have an HTTPS gateway, and you have a lookup facility that allows you to kind of find the owner of the bucket A1. So this first yellow arrow at the top implies a lookup to the cluster facility, which then says, I need to find A1, the owner of A1. Which machine owns A1? That's usually a hash resolution. Finds that place, goes and talks to it. Similar thing happens when that stateful compute cluster now talks to the storage tier, which it also finds that place. Now, something happens. That machine dies. The cluster system automatically fails over to the secondary, which has already been primed. It knows all the data, which it now gets elected to the new primary. And if that same thing happens on the storage tier, well, the same failover happens. So that's stuff that happens in these modern cluster fabrics, where stateless no longer exists. It's actually stateful is okay, because we now have ways to go and create consistency across a large cluster, so that we can go and scale those things out, because there are problems that require that. Stateless, in the sense of web server, is still very easy, but there's workloads where you need to go and maintain ownership and where you need to maintain a notion of what is what and where is where. So that was clustering. There's a fabulous talk. Unfortunately, there might not be recordings, but there's still a slide deck that's around. If you look for fiefdoms and emissaries, you will find a fantastic deck. Pat Helland wrote this. He's been fabulous in in the late 90s, transaction god, and he wrote this book. He wrote this deck about fiefdoms and emissaries, and one of the key aspects here is one around autonomy, where he speaks about how to think about autonomy and the relationship to other services. And an emissary is a very interesting concept. An emissary is a piece of software you give to someone to talk to you, and that's something that we do very, very often today by giving people SDKs. So Kafka, for instance, has a private protocol, and they reserve the right, Apache Kafka messaging infrastructure, they reserve the right to change it. The way how they get around this, around publishing the protocol effectively, or committing to the protocol, is that they ship you bits. So they ship you an SDK for this and this and this for many, many, many different languages, which are emissaries. We're going to see more and more of this in the space of IoT, because we have a notion of edge compute. We want to go and push computation out into devices that are sitting at the edge. We want to go and push compute out to fog devices, which are kind of sitting in the network. So services don't necessarily all hide behind their boundary, but they may send little software agents out into the world which kind of do work on their behalf. And if you see what JavaScript does today in browsers on behalf of the backend service, you have a lot of these emissaries. So that is also something that is an old concept, proven, because we do that all the time. The benefit of keeping these services autonomous is that they enable operational agility. Services and all the implementations can be moved or configured and replaced behind the curtain. You're committing to a contract, you're committing to a certain external facing contract. You committing means as you are upgrading, as you're changing, you keep honoring this, which buys you that sort of agility. Autonomy also, and which means not sharing stores, not sharing anything that's kind of downstream from your stack, also enables clustering. You cannot do clustering. You cannot do partitioning. You cannot do clustering. You cannot do slicing up your workload, scaling out your workload. If you share stores, if you share any downstream infrastructure with anybody else, because you don't have agility to go and change it. So that's really important. Ultimately, reusability, adaptability is something that you can achieve when you are autonomous. So autonomy is the prime principle. And if you want to take anything home from today, from this talk, autonomy is important. That is the service. What do we try to achieve? So what are we trying to ship when we ship a service? Let's go and move on from autonomy. Scalability, availability, consistency, and I don't have enough time to go and define all these in detail, so let's reliability, predictability, that's one that's easily overlooked, but someone that's actually hurting us quite a bit. If we, messages flow through our system in X milliseconds, people get really upset if it takes more milliseconds than the usual milliseconds. And if it takes like 5 seconds to go and move a message around, they call us. Predictability is really important. Predictability means you need to ring-fence resources to do the same job over and over again. There's a lot to be said about multi-tenancy and the wonderfulness of it. But if you need predictability, you need to have the resources available at all times. So that's something that's an interesting design point. We have in our service now a capability called premium messaging, where we actually ring-fence resources. We ring-fence CPU and memory for customers so that they get the same performance every time. So we don't run that in a multi-tenant system anymore in those particular cases, just for predictability. Security is obvious. Agility, the ability to go and make all the changes that I talked about. Safety, risk of disaster, supportability, cost. All of those are operational objectives that a service team needs to meet. And the service team has kind of in all those categories, you're going to get those slides, so you can go and review those areas. Makes assurances. That's the thing. So basically, in all those buckets, you think about what you are trying to achieve. And then you now turn that into an assurance to your clients, because that's part of building a service and running a service. What is my predictable performance? What is my scalability, right? If you buy X, you're getting this. And you will go and discount based on what your metrics are and based on what you measure. You will go and give yourself some wiggle room and then make a commitment to, this is my reliability. This is how many transactions I will fail. And failing transactions can be quite a bit. So for instance, what we do on our brokers is, as I said, 3 trillion transactions, close to 3 trillion transactions on event hubs per week, egress. 99.99% reliability on trillions. We have a lot of errors. We have millions of errors. Millions of errors. That's okay, because we're very upfront about what that is. You can't expect perfection out of us because we're running a system at enormous scale. But that's something that you need to be very clear about and communicate that with people. So what is your commitment? Okay. So much about services. So services is something that is really a contract that you make with other people, and it's something that's about organization. It's not about code. This is about code. Layers, tiers, and services. A layer is how you organize code. You have a notion of an interface, you have a notion of logic, and you have a notion of resource access. The reason why we introduced layers back in, there's very many of these layer patterns. MVC is one, but there's 3-tier, classic 3-tier is one. There's very many of these tiers, of these patterns, and those patterns are always for creating resiliency between those different concerns. So you can go and change, if in MVC, you can go and throw the view out without breaking everything else, right? In a classic 3-tier app, you can add another interface, you can add another way of communication without breaking everything else. You can replace the database. No, I'm joking, you can't replace the database. Many people tried. Everybody knows you can't. If you change the database, you're kind of screwed. So the rationale, and this is also why I have that circle, right? From the outside, it's more flexible. From the inside, and when you get to resource access, when you get to the database, you're super tightly coupled. But out to the edge, you can be much looser coupled. That's where you have more leverage than in the middle. That's also a reason why you want to keep those things autonomous. If you need to have a major database change, you want to constrain the impact to that one service. You don't want to go and redesign the world. So that's good hygiene in your systems. So communication layers, resource layers, and then the stuff in the middle, which is what we call logic often. Tiers are about runtime organization. This is where I might disagree with some other people who call microservices what microservices are. I have a clear distinction between service, operational assurances, contracts, teams, and tiers, which are the things that actually get deployed. For me, a gateway is not a service. A gateway is part of a service, but it's not a service per se. An HTTP API layer is not a service because it is not independent of the rest of the system, of the service that you deploy, the service that you own. For me, that's a tier. And you may able to go and independently deploy tiers, yes, but if you have to go and do magic to go and make, to do a stamp deployment of your service, you can't break anybody else, but you can completely replace all the internals of it. So tiers are about meeting your operational objectives, and that means that the gateway tier may scale higher than the backend tier might. All of your different tiers that sit in the system, that sit in your service, may have different objectives that they need to meet. So I can tell you from our service, from Service Bus, we do a lot of AMQP and HTTP traffic and a lot of crypto on the gateway. We do a lot of heavy compute work. It might not seem that way, but messaging is kind of hard. A lot of compute work in the backend, in the messaging backend. Those two tiers are completely different in terms of characteristics. And we're also, as I said, ring-fencing resources for customers. The predictability of the system depends on the messaging tier, but it doesn't depend so much on the gateway tier. The gateway tier has a completely different need for memory and CPU and networking than the messaging tier does. So we pulled them apart. We don't run them on a single set of machines. We actually run two clusters, which are effectively bound to each other and make up the service. And then we have another tier, obviously, which is the storage tier underneath it. We break those things up in tiers because we need to scale them differently and because they use the resources of the system differently. And if we have uniform usage of the resources on our machines, we actually get higher reliability. And specifically in messaging, we sell reliability as a service. So the way this materializes, as I just said, is this: gateway, backend, storage. Different tiers, one service. So layers are about code management, tiers are about runtime management, and services are really about ownership. That's that picture I have in my head. Now, I promised you communication. We have 10 minutes to go. Let's try that. Communication, messaging, is about how we move information between systems. And that's something that's really important for talking to services because services are networked entities. So let's talk about how messaging materializes. Messaging is about getting data from A to B and back sometimes. Not always. Sometimes there's a lot of here, so you have a lot of clients you have to deal with. Sometimes they show up all at the same time. Sometimes they show up in trickles. Sometimes you have enormous amounts of data that you need to go and deal with. Sometimes there are lots of there. You need to send one message. You need to get that message to a lot of people. We have one service that's called Notification Hubs that we also made, which is specifically built for the problem of, let's say, the Olympic Games or news organizations, which want to go and send one news byte, but need to get it to 15 million phones within a few seconds. Sometimes the destinations are all different. So you actually need to go and differentiate. Sometimes the destination is not paying attention or can't, so you have to do something to go and have a little mailbox for it. Sometimes the destination is super busy, so it will throw you a 503 if you try to keep tickling it. And sometimes it's just dead, and you don't know what. So there's got to be answers to those problems. HTTP, which we all use and is the de facto default for all the microservices, doesn't answer some of those questions. So let's go a little bit further and kind of think about what protocol requirements may be and what things and what many terms mean. Client and server. What is client and what is server? Client and server ultimately only describes who makes the initial connection. You have a network, someone is listening, and someone is connecting. That's client and server. Turns out and in HTTP, that's coupled, right? The whole notion of who can make a request and who can go and ask someone else is completely coupled to who makes the client connection, which is not true for many other protocols. So let's stick with client and server as just the party which is listening on the network and the party which is connecting, which is useful for many scenarios. If we think about, you have a client that needs to connect out of an environment that is firewalled and NATed and everything, but you still want to get back to them from the server side, right? It would be nice if that was possible and disconnected from the fact who's connecting out and connecting in. So client versus server is just about the network connectivity direction. Then there's directionality of that connection. Is it simplex, one way only? Some protocols do that. Or is it duplex, allowing flow of data in either direction, initiated by either direction? That's a separate concern. Then there's symmetry. AMQP, which we'll learn about in a second, is a symmetric protocol. Any of the two connected parties can do anything it likes that's defined in the protocol at all times, except connecting. Once the connection is established, it's fully symmetric. HTTP is not symmetric because only the connecting party can issue requests. That has been relaxed a bit in HTTP 2, but those are not symmetric protocols. MQTT, for instance, another messaging protocol, is also not symmetric because there's specific things that only the client can do. Multiplexing. It'd be nice sometimes to be able to go and use that same socket for two requests at the same time. HTTP can't. HTTP 2 can, because it added multiplexing, because there was realization that it would be nice to take that expensive HTTPS SSL TLS socket that has been established and reuse that instead of making many, many more for small payloads. Framing. What those protocols do is they frame the data for us, and then we take data and we encode it on top of that. JSON, Avro, message pack, XML, MQP has its own encoding, CSV, MPEG, text, raw. There is good choices for all kinds of workloads. Avro is an awesome, awesome, awesome format to encode time series data. It's binary, there's extra compression, it carries a schema with it. It's astonishingly much better, and it has a better type system than JSON, right? The world is not JSON. The reason why HTTP has a content type and why AMQP has a content type is that you can go and get to choose what you're going to go and transfer. You just need to be upfront about what you support. And then there's metadata. You want to tell the other party about what that message contains. HTTP has freely definable headers. AMQP has freely definable headers. MQTT, interestingly enough, has not. So you have to go and mangle all that information into the topic path, which kind of makes it a little weird. Or you need to have out-of-band agreements across those. So in this context, in the communication context, a service is a reusable artifact that can be accessed through channels well defined by some interface context. So that's communications focusing just on that edge. And it's focusing on that contract and that you adhere to a particular contract. Interestingly enough, no single communication mechanism fits all uses. So trying to fit everything into REST trying to fit everything into HTTP is actually not helping, but is counterproductive for many paths. And trying to make everything in JSON is also counterproductive. We have the flexibility in the stacks to actually go and use different formats for different purposes. You have an entirety that is the contract. The service has a composite surface area that is the contract you need to go and adhere to. But that may be composed of multiple channels, and it may be composed of multiple ways of how you go and encode data. So I'm going to be, well, I have still 5 minutes. Location transparency. Well, what did I just skip? Okay, that's fine. Location transparency means that you don't, that's actually a very easy one. You don't give people a direct address to your service. You hide behind at least one level of indirection. If you give someone a DNS name that then maps to where your service actually sits, because otherwise you can't move the service. There are situations that we've had in our world where we had to literally replace clusters by taking the customer data and copying it into the new cluster because our schema changes were radical. And we basically just did a re-implementation of pieces. So we kind of did a copy into the new cluster, continuous copy into the new cluster, kind of kept the system consistent, and then did a forced DNS switchover of everybody. So we dialed the DNS record to 0, the TTL effectively, in a stepwise way. Took the old cluster down, basically cut everybody's connection. Everybody failed, picked up the new DNS records. That actually works because many stacks are good about TTL. And then had everybody over on the new stack. And the only way how we can do this is to have an additional abstraction using DNS for location transparency. You know all this. You know all this. Yeah, so I mean, it's obvious that TCP is a stream and blah, blah, blah. I should have cut those slides. I just realized. Okay, so every service can be reached at least through one channel, but it can have multiple channels, and the edge is effectively the service's user interface, if you will, right? So you can have multiple interfaces to your service, and it's all just fine. So in the interest of time, let's get to the protocols. To talk about them effectively as we are now informed about them. What is HTTP 1.1? HTTP only allows the request response pattern. It's not symmetric, doesn't allow multiplexing, allows variable encodings, that's great, and allows metadata. Doesn't give you any assurances whether and when the message gets somewhere. WebSockets is not a protocol. Well, it's a protocol, but it's a tunnel mostly. If you say, I use WebSockets, then the question is, what are you going to put on top of those WebSockets? Because WebSockets is a framing protocol, and that's all it does. So anything you do over WebSockets, if you're not using anything that's a protocol that's overlaid over WebSockets, then you're using something that's proprietary. Because it's just a tunnel. It's a trick to get through 443, but it's not a protocol in itself. It just gives you a raw socket. So if you do anything just over WebSockets, you just created your own proprietary little protocol. HTTP2 is HTTP as we know it, plus multiplexing, plus binary header compression. It's no longer a very simple protocol, as HTTP 1.1 was. And if HTTP2 had come first, the adoption of that would have been very little, but now the thing has a lot of adoption, a lot of big companies behind it, and the browser vendors and the web server vendors all can collude and can go make something that's complicated, but it's effectively what we have. It has a special new feature that is a one-way communication channel that allows the server to go and send data back. CoAP is a protocol that you'll hear more about in the context of IoT, the Internet of Things, that is very much like HTTP. Interestingly, it's a symmetric, so any site can go and initiate requests, and it's super, super, super tiny. And it's being used today to go and manage all of your mobile phones. That's how your mobile phones communicate, at least in your deployments, the LLW M2M protocol, which is used for device management. You'll hear more about this if you're involved in mobile or if you are involved in IoT. And then there's MQTT, a publish and subscribe protocol, one of the messaging protocols, which is great for communicating telemetry, great for communicating little bits of data. And then there's the MQP protocol, which is a messaging protocol, which kind of sits a little bit up above MQTT in terms of capability. It supports multiplexing that MQTT doesn't. It's fully symmetric that MQTT is not. But those two protocols, AMQP and MQTT, are the two candidates if you don't use HTTP, and the two candidates for asynchronous messaging. With a broker in the middle, you can do all kinds of interesting additional things, and I'm already in overtime. I'm going to take 3 more minutes. Load leveling means the service hangs, there's a bunch of web servers here which take traffic. You have a queue. There's a lot of traffic that's coming in, and all of that lands in the queue. The nice thing is if you have a service that sits behind those, and it now pulls from a queue, that stress that comes up on the web doesn't come down into your service. Because you do a push to pull translation through the queue. That gives you load leveling. You also get true load balancing. All of the load balancers are, HTTP load balancers are actually lying to you, right? That's a lie, it's a lying term because it doesn't consider load at all, it just sprays. All mechanisms that try to do load balancing by measuring the load on a machine and then try to push are doomed to failure. The only way that really works is to pull the data, to pull jobs off a queue when your thread has capacity. So that's something that is only self-determined. So that's load balancing that you also get through a queue. So the queue insulates you from spikes, and the queue also gives you true load balancing. So that's an advantage of sitting behind the queue. And then, of course, you can go and take one message and go and distribute it to multiple parties. That is true for all those message brokers. So messaging infrastructure that you'll find that will help you with your microservices infrastructure, that will help you with meeting a lot of those operational objectives, is enterprise message brokers. Azure Service Bus, thing we build, IBM MQ, ActiveMQ, RabbitMQ. They have publish, subscribe, super robust and durable, and typically allow multi-node clustering. Then there's lighter weight message brokers like our Azure Queues or SQS that you find on Amazon. More constrained in terms of features, or Mosquito, the MQTT broker, more constrained in features in a certain way, but kind of focus on a particular task. And then we have these event ingesters like Kinesis, like Kafka, like what we have in Event Hubs, which are basically just meant to take huge amounts of data from millions of sources and capture them in the system so that they can go and be published. All of those fulfill effectively the same role. I'm going to go get to the summary because of time. Fulfill the same role, and that is being your gateway, augmenting your gateway for your service. So they sit up here. They're message brokers. They're not clever. They're not the ESB. You can go and set up a queue over here. You can set up a queue over there. You can set up a queue over there. All of those you can treat as one because they have no intelligence. They don't touch the payload. Right? They're just dumb pipes, and that's good that way. But they take the traffic for you so that you can go and pull it into your service and handle it. That you can fulfill your operational objectives. That you don't get punished by the stress that comes in from the outside world. And that you can go and make sure that a message has been captured reliably, that you never lose that message. You have never any doubt as you have with HTTP. HTTP is always great, and all these synchronous protocols are always great if you need to have an ad hoc response to something, if you need to know. Often it's enough to know that the message has been submitted and the message will later be published. And that's something we see more and more and more. So when you think about microservices, think about autonomy, driving principle. Second, think about all the different options you have in terms of protocols and encodings, because they are all part of your arsenal. Don't let yourself be constrained to just HTTP and JSON. And that's what I had. Thank you.